Hello everyone. So in this video what we will discuss? We will discuss about the infinite current through the capacitor. So till now what I have told you is that the capacitor has a property that it doesn't change its voltage immediately. The voltage it is having at t equals to 0 minus, it will have the same voltage at t equals to 0 plus. Okay. But this is the case only when there is a finite current. Right? I told you this thing. I emphasize on this point as well. Finite current. Now, what do you mean by infinite current? So, I have already told in the basics. What do you mean by infinite? If something is infinite, that means it is impulsive. Right? That means just for a moment it came and then went off. It will come and went off. If there is something infinite, it can't be there for all the time. Like it cannot happen that it is there at t equals to 1 and it is there at t equals to 1 plus as well. If it is there at t equals to 1, that means it will be there for t equals to 1 only. It won't be there for t equals to 1 plus. That's why when we make the graph of delta t, we make it like this. Right? Just at t equals to 0. Not at t equals to 0 plus. At t equals to 0 plus, the value is 0. And that's why we define the delta function like this. What is delta function? Delta function will give the value at infinity only at t equals to 0. Apart from t equals to 0, it is always 0. Right? So now what I am doing, I am forcing an impulsive current in the capacitor this time. And I will write down the equation of VCT. Because what we have studied that voltage cannot change. Right? So tell me one thing, what is the value of VC0 minus? That is 0 volt. Now let's find the value of VCT. Let's find VCT. Okay. VC0 minus you know. Okay, you don't know this. Let's just forget it. Now I will just write VCT. Okay. Let's just forget VC0 minus. So I will just write VCT. So it will be 1 by C integration minus infinity to t I of t dt. This is the expression, right? What is the expression of I of t? I of t is I naught delta t. Right? I of t is I naught delta t. I naught delta t dt. I naught is a constant term. It can be taken outside. I naught by c minus infinity to t integration of delta t ut. Tell me what is the integration of delta t? What is the integration of delta t? Integration of delta t is I naught by c ut. Right? Integration of delta t is ut. I have told you the integration of impulse will be step, integration of step will be ramp, and differentiation we will go from this side. Differentiation of ramp will be step and differentiation of step will be impulse. So what do you get the expression? The expression of VCT came out to be I naught by C ut. So it came out as step. So now if I make the graph of VCT, so what is happening? How do you make the step graph? 0. For t less than 0 it is 0. And then suddenly it goes I naught by C. Right? Now tell me one thing. Here IT is I naught delta t. Right? So what is I naught? I hope you all will be able to tell me what is I naught. Is it a current or charge? I naught is a current or charge? It is charge. Why so? Because the unit is ampere into second. Right? So it is a charge. Right? I have told you I naught is not the magnitude, it is the area, and area is current into time. So ampere into second. And what does ampere into second give you? Coulomb. Right? Because I is dq by dt. If dt goes here, so ampere into second will give you Coulomb. So this is charge. So what do you mean by an impulsive current? I have already told this fact. What do you mean by an impulsive current? That means in 0 time you are giving I naught amount of charge to the capacitor. Right? So if I am writing I naught delta t, so what does that mean? You are giving I note amount of charge, in no time, right? So what is the value of charge q? Charge q is I naught. What is the value of capacitor? Capacitor C is C only, right? So what will be the voltage? Voltage V will be Q by C. That means I naught by C. So here you can see what is the voltage, I naught by C, right? And what do you see here? What do you see here? VC 0 minus capacitor voltage is VC. Okay. VC 0 minus was 0 volt. Now what is VC 0 plus? Tell me what is the value of VC 0 plus? VC 0 minus was 0 volt. What is the value of VC 0 plus? That is I naught by C. This was just another way. Okay. I will just call this method 2. Okay. This was just a method 2 to tell what will be the VC waveform. Okay. This was the equation, and this was like, you can think I naught amount of charge is given and capacitor is C. So what will be the voltage? I naught by C. So here VC 0 minus was 0 volt and VC 0 plus is I naught by C. So what do you understand here? What do you understand? The capacitor doesn't follow its property of not changing the voltage immediately in case of what? In case of impulsive or infinite current. So what do you understand by that? Whenever there is an infinite current in the capacitor can change its voltage immediately. Okay, so I will write it and I will just pause the video and will write it. Okay. Okay, so I have written a very important point, that is, whenever there is an infinite current flowing through the capacitor, it will change its voltage immediately from 0 to some value. Okay, got it? Now let's see this question. We have seen this question in basics of network. If I haven't taught you the concept of transient and concept of capacitor, if I had asked you what is the value of VC2, what would you say? C1 upon C1 plus C2 into 5, right? Right? If you remember the basics, in basics we just divided the potential, considering this has the impedance of 1 by omega c 1 by j omega c2, and this has the impedance of 1 by j omega c1. So we just divided it in the inverse proportion, right? But here we will see what is actually happening. So let's just make the circuit. Let's just make the circuit once again. I'm just making both of the terminals as grounded, because if this is grounded, this will be also grounded, this will be also grounded. So like this I am making. This is C1, C2, this is VC1, and this is VC2. And here I will write 5 UT, right? So if you can tell what is VC2, VC2 will be C1 upon C1 plus C2 into 5, right? But let me show you one thing. Now, circuit initially. So tell me what will happen initially at t equals to 0 plus I am talking about, okay? At t equals to 0, sorry. This is the voltage source we are having, right? Now, this is shorted and this is also shorted, because both of the capacitors are having no voltages. Even if they were having voltages, they would be replaced with the voltage source. Let's assume if C2 was having 3 volt, it would be replaced with the voltage source of 3 volt, right? And now I will just write 5 here, okay? 5 volt. Now tell me what is the value of current? IC. What is the value of current? IC. That is 5 by 0. No impedance, short circuit path, 5 by 0. That means infinite current, right? So what will happen? Capacitor will change its voltage immediately. its voltage immediately. How they will change? They will just divide it in inverse proportion. Why is it happening? Because the current is same. In both C1 and C2, the current will be the same. Whatever the current is, infinite current is there. We will find the value of current as well. So we need to comment on VC1, VC2 and IC. I will just make IC. What will be VC1, what will be VC2 and what will be IC. So we need to comment on these three things. So since both of them are connected in series, that means both of them will be having the same current. That means both of them will be having the same charge, right? If both of them are connected in series, that means both of them will be having the same charge, right? So we will just divide the voltage in inverse proportion, or you can see what is the impedance provided by the capacitance. It is 1 by j omega c. So if we just divide it in inverse proportion, it would be j by omega 1 by j omega c upon 1 by j omega c plus 1 by j omega c2. So it would come out to be c2 upon c1 plus c2, right? Just like resistors, we can divide it, right? So I will just write this is method 1 of solving. Why I am not able to make a straight line? C1, C2. By the way, it's Diwali today. Here. Okay, this video will not be uploaded on Diwali for sure. This will be uploaded later on. But today, this is Diwali. Yeah, just wanted to share. So what will be your VC2? Tell me. It will be 5 into C1 upon C1 plus C2 into UT. What is VC1? What is VC1? Inverse proportion. 5 C2 upon C1 plus C2 into UT. Now what will be the current? That I will tell you. Okay. No worries. That I will tell you. Or here only I can tell. What is current? IC. What is current? IC. It can be C1 dVC1 by dt. Right. Just the differentiation. Or it can be C2 dVC2 by dt. Right. So I will just solve this one. C1 into differentiation of this. Tell me what will be the differentiation of, yeah, this is VC1. What will be the differentiation of this? This is just a constant value, right? This is a constant value. So I can write A into UT. What is the differentiation of A into UT? It is A into delta T, right? Differentiation of UT is A into delta T. So simply the differentiation would be 5C2 upon C1 plus C2 into delta T. So what will be your IC? IC will simply be 5 C1 C2 upon C1 plus C2 into delta T. So this is the impulsive current we are having, right? Now we can make the graphs as well. For VC1 we can draw, for VC2 we can draw here, and for IC we can draw here. VC1, this is VC2, this is IC. What is VC1? Initially it is 0, then it went up, went like this, right? So this value is 5C2 upon C1 plus C2. Always remember you have to divide it in inverse proportion. Okay. Sometimes I have seen students dividing it in not in inverse proportion but in the proportion. But this should not happen. You should divide it in inverse proportion, right? So it would be 5C1 upon C1 plus C2. And what is the value of IC? This is an impulse. The value is 5C1 upon C1 plus C2. So this is an impulsive current we are having. So these are the three graphs. So graph I will not make again and again, but I will tell you another method as well. Also you can comment on the graph by seeing the waveform as well. Like if you know the waveform of VC1, you can make the graph of IC as well. How? Just you know the waveform. So you are seeing that from 0 it is charging to some value, right? From 0 to suddenly the voltage is rising. So if suddenly voltage is rising, what will be the differentiation? Differentiation will be impulsive. So if you are given a voltage waveform and they ask you to comment on the current waveform, so you can do that, right? They have given the voltage waveform, so from here to here you can come, because you simply know IC is equals to C dVc by dt. Just the differentiation of the voltage waveform into the capacitance value. Differentiation of voltage waveform into the capacitance value, that is the current of the capacitor. So that you can do, right? Now let's talk about the method 2. Okay, let me add a page. Okay, so let's talk about method 2. Okay, so this was your circuit 5 ut C1 and this is C2. Here we will use equations actually. Okay, this is VC1, this is VC2. Okay, one thing you know, C1 C2 are in series, C1 and C2 in series, that means current same, that means current same, and that means charge same, right? If charge is same, that means I am saying Q1 equals to Q2, that means I am saying C1 VC1 is equals to C2 VC2. This is equation 1. What is the second equation? Second equation is 5 ut is equals to VC1 plus VC2. So from here you can get the value of C1, right? Value VC1 value would be C2 VC2 by C1 plus VC2. So what will be the value of VC2? Value of VC2 would be 5 into C1 upon C1 plus C2 into ut, right? And what will be the value of VC1? That would be 5 C2 upon C1 plus C2 into ut. So by this method also you can solve, right? So this is also one method. Okay, so I hope you have understood my point here. The point I wanted to deliver here is that whenever there is an infinite current flowing, how will you check the current is infinite? By drawing the circuit like this. We drew the circuit here and we got to know that the resistance is 0. The resistance provided by the capacitor is 0. If the complete resistance in the circuit is 0, that means there will be infinite current. So if there is infinite current, there will something happen. And something, what will happen? The capacitor will change its voltage immediately. Okay, so this is the point I wanted to deliver here. Now let's see one more important point. This is a important concept of step function. Okay, so this is a step function, right? This is our step function, right? For t less than 0, what is step function? This is ut. So it is 1 for t greater than 0 and it is 0 for t less than 0. Now we will talk about at t equals to 0. At t equals to 0. So just see one thing, at t equals to 0. At t equals to 0, it will provide you infinite frequency. Why so? Because I have already explained this concept in basics of basics of signal sensing systems. Okay, if you don't know why it is infinite frequency, you just go to the basics of signal system video and you will get to know there. Okay, I will just talk in short, because from 0 to suddenly it is rising to A. If it is rising slowly, that means it has omega frequency. If it is rising some faster, that means it has frequency greater than omega. If it is rising in no time to A, like from 0 to in no time it is rising to A, that means it is having infinite frequency. So if it is having infinite frequency, so if we talk about the capacitance provided by the resistance provided by the capacitance. If we talk about the impedance, I should write impedance provided by the capacitance. Okay, so if we talk about the impedance that is provided by the capacitance, so tell me what will be the value? Zc will be equals to 1 by j omega c. That means 1 by j, omega value is infinity, c. So I can write nearly 0 or I can write very low, right? So what do you understand? At for step function, I think I should keep it a bit down now. So what do you understand by this point? Note, very important note, okay? For step function at t equals to 0 or omega equals to infinity, the the capacitor provides very low impedance. Are you getting this point? If there is step function applied, that means it has at t equals to 0 it has infinite frequency. Infinite frequency means 1 by j omega c, infinite means very low. So if frequency is very high at t equals to 0, that means capacitor is providing very less impedance, right? So here the capacitor will provide very less impedance. Now if two resistors are connected in parallel, let's assume one is having a value of 1000 and one is having a value of 1. So what will be the equivalent? It will be near to 1, right? You know it, right? It will be near to 1. What will be the equivalent of this? 1000 into 1 upon 1001. So it will be near to 1, right? So you can replace the parallel combination of RC with a single capacitor. Do you agree to my point? And you can replace this with a single resistor. Why so? Because if 1000 and 1 is connected in series, it will be nearly equals to 1000 only. So this is some finite value and this is very low value. So if very low and finite value is connected in parallel, it will be replaced with a very low value. If very high value and some very low value, some finite value and very low value are connected in series, that means it will be replaced with the finite value. So at t equals to 0, you can replace something like this. And further you can replace the capacitor with short circuit depending on the circuit. We will see the circuits, then you will get to know whether I should replace it with short circuit or I should keep it like capacitor only. Okay. So that's why we saw this circuit now, RC circuit, and there was a step input applied. So what did we do? We said that there was zero voltage across it, so we replaced it with the short circuit. This is also a good concept, but there is also one more concept that at t equals to 0, we are having infinite frequency. So because of infinite frequency, this will be replaced with a single capacitor only. This R and C combination, what I wanted to say here is that, let me just redraw it, okay. Let me just explain it with an example. So what did we do? This was our step function applied. So what did we do in this problem? At t equals to 0, what did we do? We just said this will be R will be there and this will be replaced with short circuit. This circuit we made, right? Now what I am saying, at t equals to 0 we are having infinite frequency, and because of infinite frequency this will provide very less impedance. So this series combination of RC can be replaced with R only. So let's see. This is what we did there. While understanding this circuit, I told you there was no voltage on the capacitor, so you can replace it with the short circuit. That was also a good concept. That is also fine. But also we can see by this thing, if we are applying the step input, that means we can replace the capacitor, we can replace the series combination of resistance and the capacitor with a single resistor only, and this is what we did here. Are you getting my point or not? So the previous circuits that we have solved, you can analyze those circuits with this analysis. Okay. Okay. Now let's talk about steady state at t equals to infinity. So what do you mean by steady state? At t equals to infinity, the frequency is 0. Okay. At t equals to infinity, at steady state. This was our step function. This was our step function, right? So at here it is omega equals to 0, steady state. Okay. At steady state you will have omega equals to 0. That means it is nearly equals to infinity. That means very high, right? Very high. So what do you understand by that? What do you understand by very high? Yeah, so that means capacitor provides very high impedance at steady state, right? So if it is providing very high impedance, that means what will happen? The parallel combination of RC will be replaced with a single resistor only, because this is a finite value. Let's assume this is 500 and this is very high, that means this is 1 mega ohm, so will be replaced with the lower value. So what is the lower value? That is resistance, right? And what will happen to this series combination? It will be replaced with the capacitor only, right? It will be replaced with the capacitor only, because this is very high. Furthermore, it can be replaced with open circuit as well, right? But depending on the circuit. So this is an important concept that will be used in the further analysis. So I have told you, at t equals to 0, capacitor, you don't need to mug it up. You will just see step function. Okay, at t equals to 0, infinite frequency, that means capacitor is providing very less impedance. If capacitor is providing very less impedance, that means the parallel combination of RC can be replaced with the capacitor, and series combination of RC can be replaced with the resistor only. And at t equals to at t equals to infinity and steady state, frequency is 0. If frequency is 0, that means the capacitor is providing very high impedance. So parallel combination will be replaced with the resistance only, and the series combination will be replaced with the capacitor only. Are you getting my point? No need to mug it up. This was just a concept. You can think it in real time only. Whenever the interviewer is asking the question, or whenever you are solving it in the exam, you can think it there only. Okay, no need to mug it up. Okay, so while going to the next analysis, next question actually, or next circuit, we will study the basics of Laplace transform. Now why it is important? Look, the interviewer doesn't expect you to solve the circuit by Laplace transform. Also in the exam, if you need to solve it very quickly, you shouldn't use Laplace transforms, because it makes the problem very mathematical. Like, you don't need to think. When we will solve the circuit, you will get to know. If you are solving the circuit by Laplace transform, you won't need to think anything. Okay, you will just replace the circuit and just do mathematical analysis, that's it. But what they expect a intuitive approach, right? And also if you are doing it for exam or gate exam or anything, there also you will try to solve the question very quickly. So I will tell you both of the method, by intuition as well, or how to solve the problem quickly, also by Laplace transform as well. So you should know Laplace transform as well. Like, if there is very complex circuit that you can't solve, so eventually you will solve it with Laplace transform, because it makes the circuit pure mathematical. So we will study the basics of Laplace transform. So what is Laplace transform actually? So whatever we are doing all this thing in time domain, right? These things, time, everywhere there is time. I think I should write it Vc2 t, Vc1 t. Okay, because all these are function of time. Okay, I should have written here t. Okay, so all we are doing in time domain only. So what does Laplace transform do? It converts it into frequency domain. That's what you need to remember. Okay, it converts the time domain into frequency domain. Very deep analysis of Laplace transform I will teach you in signal systems, and I will teach you very deeply. Okay, you will understand the real difference between the Fourier transform and Laplace transform, that we will see in signal systems. But here, for network purpose, time domain to frequency domain, that's what you need to remember. And S is equivalent to j omega. Actually it is equivalent to sigma plus j omega, but we will understand this point in signal system. So for network analysis, you just need to know the S is equivalent to j omega. Okay, like, we can't really go deeper into the concept right now. I hope you understand the concept. And in the interview, no one will ask you what do you mean by S plus j omega or anything. In the interview of analog domain and all these kind of things, they don't ask you. Okay, that much deeper knowledge. In signal system, I will teach you. Okay, so S is equals to j omega. And this is the Laplace transform. Okay, this is the Laplace transform. I should write here Laplace transform of xt. What is the Laplace transform of xt? That is x of s, that is minus infinity to infinity, x of t e to the power minus st into dt. Mark it, it is minus infinity to infinity. Okay, it's not minus infinity to t, minus infinity to s. It is minus infinity to infinity, complete in time domain. Okay, and then it is like, this is just a way of writing that Laplace transform of xt is x of s. Okay, Laplace transform of xt is x of s. Okay, now let's find the Laplace transform of ut. So I am saying that my xt is ut now. Okay, So Laplace transform of xt will be equals to x of s, right? So what is x of s? X of s is minus infinity to infinity xt e to the power minus st into dt. Minus infinity to infinity. What is xt? Xt is ut, right? Xt is ut. Ut e to the power minus st into dt. X of s. Now ut is defined from, this is ut, right? Ut is defined from, this is a value 0 to infinity only. So I can write 0 to infinity and value of ut is 1 e to the power minus st into dt. X of s minus 1 by s e to the power minus st 0 to infinity. So minus 1 by s e to the power minus infinity minus e to the power 0. This value is 0, this value is 1. So eventually you are getting 1 by s. So what is the Laplace transform of ut? So from here you can see Laplace transform of ut is 1 by s. Let's assume if there was a constant, let's assume if it was aut. So what would happen? A would come out. Here you would written aut, a is constant, so it would come out of the integration. So a would be outside. So you would get answer a by s. So what is the Laplace transform of aut? It is a by s. Okay, right? So we won't solve for all these in network in signal systems. We will solve for everything. Okay, you can solve it on your own as well. Like for ut, what will you do? You will write t here. Sorry, for rt, a into rt, what will you do? You will put a outside and rt will be t from 0 to infinity. From 0 to infinity it will be t, right? For delta t, what you will write? For delta t, you will simply write delta t, and I have told you the integration of delta t. What is the integration of delta t? E to the power minus st dt. So for the integration, you need to write it like this: t minus 0 e to the power minus st into dt. So it is defined only at t equals to 0. So this 0 will go here. So it will become e to the power 0. So it will give you answer equals to 1, right? So that you can do. Okay. So in that way you can solve. Okay, so I will just write down the final answer. You just need to remember the final answer. What is the Laplace transform of a into ut? That is a by s. What is the Laplace transform of a into rt? That is a by s square. What is the Laplace transform of delta t? Laplace transform of delta t is 1. Okay, so it will be a only. So from delta t to you are going to ut, from there you are going to rt. Okay, so first one is 1, then 1 by s, then 1 by s square. So that's how you can remember. Okay, and I hope you have understood the integration concept. Let me tell it more deeply. Let's just assume you are integrating in this way. Okay, you are just integrating this function, or let's just take 0 here. Okay, how do you integrate a impulse function? I am telling you. Okay, so you will see this is defined only at t equals to 0, right? This is defined only at t equals to 0, and my other function is e to the power minus st, that is something like this. So now if we multiply these two, here there is multiplication, so if we multiply these two, only the value will come. Let's assume the value here is, why to assume the value here is 1 only, right? So value here is 1 only, so I am just putting 0 in this function, right? Because it was defined at t equals to 0 only. So if I put e to the power minus s 0, so I will get this value. So if you multiply these two, let's just assume it is having value a. If you multiply these two, a into this, so what will you get? An impulse of a only. If we were having 2 here, so what would you get? A into 2, so an impulse of 2a. So just your impulse is getting multiplied at the point where it is defined. So it is defined at t equals to 0 only, so I am just putting in the function t equals to 0 and getting this value. So finally you will get 2a delta t. Here your a value is 1 only, and this value is also 1. So what you will get? You will get simply delta t, right? So this much of thing, this complete thing can be replaced with 1 into delta t only. So now your function becomes minus infinity to infinity delta t into dt. And now tell me, what is the differentiation of, so what is the integration of this? That is ut, or you can simply write 1, right? Because minus infinity to infinity, so you can write it as 1. Okay, so eventually you get the final answer as 1 only, and if there was a constant, so you could write it outside. Okay, so this is what is happening. And why did I write ut as 1? Because when you are talking about the Laplace transform, it is only defined from 0 to infinity in case of network analysis. Okay, if it was defined from minus infinity to infinity, the case would have been different, but here we are defining it from 0 to infinity only. Okay, for right-handed signal only we are defining, so it is let's assume ut as 1 only. Okay, but ut is not 1, because 1 means from minus infinity to infinity it is always 1, but ut means from 0 to infinity it is 1. So there is a big difference, but for now just assume ut is 1, because we are not really going deeper into the concept. We are just understanding what is whatever that is required. Okay, for network analysis. So for network analysis you just need to know what is the Laplace transform of del t, that is 1. If a is there, so constant will come outside, and that will be a into 1, so it would be a only. Now what is the Laplace transform of e to the power minus at into ut? That is 1 upon s plus a. Okay, so this is very very important, you need to remember it. What is the Laplace transform of cos a at into ut? Just mark everywhere ut is added. Okay, everywhere ut is added. So what is the Laplace transform of cos at into ut? It is s upon s square plus a square. Okay, and what is the Laplace transform of sin at into ut? It is a upon s square plus a square. So this is the major difference. At for cos you will have s upward, and for sin you will not have s upward. Okay, so that is the major difference that you need to remember. Okay, these two are important as well. When we study LC oscillator, these will be used. Okay, and what is the Laplace transform of x1t plus x2t? That is x1s plus minus x2s. What is the Laplace transform of xt into xt t minus t naught? Laplace transform of xt is x of s. What will be the Laplace transform of t minus t naught? That will be e to the power minus s t naught x of s. Laplace transform of xt is x of s. What will be the Laplace transform of x t minus t naught? That would be e to the power minus s t naught x of s. Okay. Okay, let's move on to the next property. It is actually written the integration. Okay, we are talking about the integration here. So if xt is the Laplace transform of x of s, then it will be x of s by s. Okay, if you know the Laplace transform of this, then you can write down the Laplace transform of complete integration as well. So just integration will bring 1 by s. Okay, now tell me what will differentiation will bring? Differentiation will bring x s. Okay, it will bring s. Okay, integration will bring 1 by s. I will just write it down. Okay, integration will bring 1 by s. Mark the thing that it should be from some value, let's just assume minus infinity, to some value t. Okay, the integration should be like this, and d by dt will bring s. Okay, now d square by dt square, it will be like this: x square x of s minus s x of 0 minus x dash 0. Or I should write small here, because x of 0 means x of 0 minus x dash 0. Why I am writing small? This is, what do you mean by x of 0? What do you mean by x of 0 here? What do you mean by x of 0? X t equals to 0. Okay, not x s equals to 0. Okay, just understand this point. Here we are writing x t equals to 0. Okay, let's just assume we will take an example for this. So I will add a page. So we already know example we are taking. Okay, so before taking the example, let's just see this form. Okay, what is this form? Laplace transform of dn x by dt. Just we are differentiating here once, here twice, and here we are differentiating n times. So just see this formula. You don't need to mug it up. First, s to the power n x of s minus s to the power n minus 1 x of 0 minus s to the power s to the power n minus 2 x dash 0, and then here we are differentiating 9 minus 1 times. Okay, so like if there was differentiation was done twice here. Okay, here the differentiation was done twice, so eventually we are differentiating only once. And what do you mean by x dash 0? That is also important. Okay, what do you mean by x dash 0? That is dt by dt x of t at t equals to 0. Okay, let's just assume if your xt is 5t. Okay, now someone will ask you what is the value of x dash 0. So what will you do? Tell me. X of 0, what is the value of x of 0? Now differentiate it. X dash 0, that is 0. This is wrong. First you need to differentiate. What is the differentiation of x dash t? That is 5. Now put 0. X dash 0 is 5 only, because it is always 5. So this is the correct answer. Okay, x dash 0 is 5, not 0. If you don't know this thing, you can write it in some box and keep it there. Okay, first you will not put the value. First you will differentiate, then you will put the value. So this is what I am meaning here. First differentiate, then put the value. Okay, and for understanding this, I will take an example. Okay, so Laplace transform of RT, you tell me what is the Laplace transform of RT? That is 1 by s square. Now what will be the Laplace transform of ut? That I need to find. Okay, so what I will do, d by dt of RT is ut. D by dt means s will be added upon s square will be the Laplace transform of u of t. So from here you are getting Laplace transform of u of t will be 1 by s. Okay, okay, so in most of the cases what happens is that these condition will not even come, because there will be no initial condition. Your x of t would be 0 for t less than 0, like there would be no initial condition. Even if there is an initial condition, then only these things will come. Okay, so you will not have to use these examples. Actually you will only have to use this term, the first term only. Okay, if thrice differentiation is done, s square x of s. If 4 times differentiation is done, sorry, x cube, sorry, if 4 times differentiation is done, s to the power 4 x of s. If 5 times differentiation is done, x to the power 5 x of s. Once differentiation is done, x of s into x of s. Okay, so you won't have to use this one further, but just to you should know these basic things, so that's why I am telling. Okay, okay, so now what is the Laplace transform of e to the power minus at into x of t? It will be x of s plus a. We can understand this with an example as well. Like what is the Laplace transform of ut? That is 1 by s, right? What will be the Laplace transform of e to the power minus at into ut? It would be x of s plus a. If x of s is 1 by s, what will be x of s plus a? It would be 1 upon s plus a. Also, you also know e to the power minus at into ut. Here only I told you Laplace transform of e to the power minus at into ut is 1 upon s plus a. Also by property here as well you can see by this property. Laplace transform of ut is 1 by s. So Laplace transform of e to the power minus at into ut would be 1 upon s plus a. Right? I hope you understand this concept. Now this is an example we are taking. No, not the example. So Laplace transform of t into xt, that would be minus d by ds x of s. Okay, this would be minus d by ds x of s. Now here we can take an example. Laplace transform of ut is 1 by s. What will be Laplace transform of tut? Or what you can say, Laplace transform of RT, right? So Laplace transform of tut would be minus s d, sorry, not minus s, it would simply be minus d by ds into x of s, that is Laplace transform of ut. And what is the value of Laplace transform of ut? That is 1 by s. So it would be 1 by s square, right? So Laplace transform of RT is 1 by s square. Just the Laplace transform of this value, t into ut, Laplace transform of this and the differentiation, right? So Laplace transform of this 1 by s into the and the differentiation, that would be 1 by s square and minus sign also. So Laplace transform of RT is 1 by s square. So this is an example only. Okay. Also, why am I taking this example? Because you need to remember this. Okay, if you remember this, it is very good. What is the Laplace transform of t into e to the power minus at into ut? Also, you need to remember from left to right, also from right to left as well. Okay, like if they have given 1 upon s plus a, so you should be able to tell it is the Laplace transform of e to the power minus at into ut. If they are giving a upon s square plus a square, you should be able to tell it is the Laplace transform of cos at into, sorry, sin at into ut. Okay, if it is given a by s, you should be able to write a into ut. Okay, so if this is given, what will be the final answer, that we will see. So differentiation of the Laplace transform of this value, so it would be minus d by ds 1 by s plus a. So what would you get? Final answer as 1 by s plus a square, right? So what is the Laplace transform of t into e to the power minus at ut? That is 1 upon s plus a whole square. Okay, so you should be able to write in the both way. If somewhere it is written 1 upon s plus a square, so what should click in your mind? T into e to the power minus at into ut. If somewhere 1 upon s plus a is written, what should click into your mind? It should be e to the power minus at into ut. If somewhere 1 upon s is written, that means it is ut. Okay, so these things should click in your mind. Okay, so just see the picture once again, it will be all clear to you. You won't need to mug it up. Okay, because you will be using it more and more time in your complete preparation, so it will remain there in your mind. So you just don't need to mug it up currently. If we will solve the circuit, so it will be in your mind later on. Okay, so now we will solve one circuit using Laplace transform only. Okay, but before going to that, we should know how the circuit elements will behave considering the Laplace transform. Let's just assume there is a resistor, so how will I make it in the Laplace transform? Okay, so before going to the analysis, just tell me one thing. What do you mean by Laplace transform? From time to frequency, right? Is resistor anyway dependent on time? Let's just assume you at 1 o'clock, the value of your resistance is R for a step input. If you apply the ramp input at any time at 2 o'clock, the value will be R only. If you apply an input like this, something like this, at any time, your value of resistance will be R only, right? If I am writing 5 ohm, that means 5 ohm for any kind of input. At any time, at any frequency, it will be always 5 ohm. At any frequency, any time, anything, it will always be 5 ohm, right? That means it is not dependent on the time. Resistor is not a function of time, right? So the impedance provided by the resistance, that is equals to R, is not a function of time. So this will be replaced simply by the resistance only. So no changes will be done in case of Laplace transform. Or also you can see here, Vt is equals to It into R, right? So Vt by It is equals to R. That means Zt is equals to R, right? So basically your Z of S is taking the Laplace transform, it will be R only, because it is just a constant value which is not dependent on the time. So the impedance provided by the resistance will be R only. Okay, now let's talk about the capacitor. Okay, so first we are assuming the capacitor is having no initial voltage. That means Vc 0 minus is 0 volt. Okay, now let's talk about the equation of Vct, or I can write equation of Ict. So Ict is C dVct by dt, right? So capital I, capital I, capital ICT. So if I am writing capital ICS, it would be C into s vc of s minus the value at t equals to 0, right? What did I write here actually? Okay, here I wrote it wrong. S x of s minus the value at x equals to 0, okay? X t equals to 0 minus value x 0, okay? So this also comes here, okay? Now what is the value of this? This is 0 only. This is time domain. I am writing about VCT, okay? So this is 0 only, right? So what do you end up with? CS VCS, that is your ICS. So if I am talking VCS by ICS, that means Z of S, that is equals to 1 by S. What is this? This is impedance provided by the capacitor in Laplace transform. Impedance provided by the capacitor in Laplace transform. This is the value, right? Okay. Now the capacitor is having some initial voltage. So what will happen now? ICS would be C, sorry, not C, CS, right? C, yeah, it would be C S VC of S minus value at, okay, this is VC we are talking about, VC, time domain value at t equals to 0. So C S VC of S, what is the value at t equals to 0? There is something wrong, I guess. Yeah, it's fine, no problem. So it is V naught. So it is having initial voltage of V naught. Okay, so that is IC of S. Let's just forget it. So what will be your IC of S? That would be CS VC of S minus CV naught. Okay, now I need to find VC of S upon IC of S, right? So I just need to find the value of VC of S. So I am writing CS VC of S is equals to IC of S plus CV naught. Is that fine? It is fine. So VC of S is equals to IC of S upon CS plus V naught by S, right? So this is the final formula. So what is this? From here what you can understand is that, from this term you can understand is that here your VC of S upon IC of S will give you 1 by CS. So basically the impedance will be 1 by CS, but along with that we will have a voltage source as well. Are you getting this point? Let me show it in the next page. Okay, I will have to add up a page. Basically this is the summary, that is, if your capacitor C is having an initial voltage of V naught, so what will you do? You will first, what we are doing here, impedance in Laplace domain, So what you will do, you will first take out the voltage source, and get its Laplace transform, okay, and then just replace the capacitor with 1 by CS. Just take out the voltage and take the Laplace transform, that means V naught by S, okay. It is just V naught, you can consider it as V naught into UT, because we are talking about t greater than 0, so you can consider it as V naught into UT. So V naught, what is the Laplace transform of UT? That is S, okay. So sometimes people forget putting this 1 by S, so you shouldn't forget this 1 by S, okay. Now tell me one thing, can you apply source transformation here? Source transformation, okay, this page will go blank only, so I can apply like this, source transformation. So how will you apply source transformation? Let's just assume if you are having a voltage source of V and a resistance R. So what was the transformation? A current source of V by R in the direction from getting out of positive, right? Current source of V by R and in parallel with the resistance R. So this is the transformation, right? So this is what you will do here, right? So this voltage source, this is a voltage source and this is a resistance. So the current source will be V naught S upon the resistance, that means into CS. So the current source value will be CV naught. CV naught in parallel with the resistance, that is 1 by CS. Okay, that is 1 by CS. So that's how you can replace it as well. If I am telling A, B, this is A, B. And tell me one thing, what will be ICS? This will be ICS, right? This will be ICS, and here as well this will be ICS. What will be VCS? So this complete circle will be VCS. Okay, I think I should need, or I can, what I can do, I can do this. So this complete circle will show VCS, right? And here also this will be VCS. This will be this is not looking nice actually. Let's just forget about this folks. So you can tell me this will be your VCS, right? VCS, and this will be your VCS. So if you write down, if you want to write down the equation from here, what will you write? VCS by 1 upon CS. Yeah, so that is outward current plus that is IC of S, sorry, plus IC of S is equals to CV naught. Did I write it right? Did I write it correctly? ICS is equals to CSV of S. So IC of S will be in this direction. Let me check it. Yeah, okay. So actually I made the direction wrong, right? This direction is wrong actually, right? Because here what I have seen, that current is getting into the capacitor. VCD is plus 2 minus, the current is getting into the capacitor, right? So the current should get into the capacitor, not flow out of the capacitor. So this will be IC of S, right? This will be your IC of S, right? So from here, what do you understand? VC of S into CS is equals to IC of S minus CV naught. Just as applying simple KCL KVL. So IC of S is equals to VC of S CS plus CV naught. This is the final answer, right? Like this is the final expression. From here as well you can see the expression. So in conclusion, you just need to know how to replace the capacitor with its equivalent in the Laplace transform. Just get the voltage and replace it with the battery of V naught by S and replace the capacitor with 1 by CS. Okay, here also you can write down the equation actually. So your VC of S is equals to V naught S plus current into this resistance, and that is IC of S by SC. So this is what we were getting here. VC of S is equals to IC of S by SC plus V naught S, and this is what we are getting here, right? So in conclusion, you just need to know how to replace voltage V naught by S, capacitance 1 by CS. Also, what do you know? What is the resistance provided by the capacitance? That is 1 by J omega C. This is the impedance that is provided by the capacitance, right? Impedance provided by the capacitance, that is 1 by J omega C. Just replace J omega with S, that is 1 by C. Now think about inductor. What is the resistance provided by the inductor? That is J omega L. Just replace J omega with S, so it would be LS, right? So this is the summary you need to remember. This is the important form. Okay, this is the voltage one is an important form. Okay, now talking about the inductor. Okay, so the current that is coming here is IL into T. Let's just write down the expression. VLT is initially no current is there. Like in the capacitor, what did we saw? Initial no voltage. So here what we are seeing, initial no current. So it will be L into DILT into dt. DILT by dt. Okay. So VLT L S ILT, sorry, not ILT, S IL of S minus the initial. Actually here in the time domain, if I am writing, no, I should have written it in the, not in the capital letter, in the small letter I should write. Why you are understanding my point? No, because if I am writing Laplace transform in capital letter, then I should write this one in the small letters actually, because Laplace transform is written in the capital letter. So I should write in the small letter. So the Laplace transform will be capital capital IL of S into minus IL of 0. So this value will go down to 0 only. So basically you, and this is not VLT. What I am doing, man? This is the Laplace transform I am taking. So VL of S is equals to LS IL of S. So from here VL of S by IL of S, that is equals to Z of S, that is equals to LS. Okay. So this is the impedance provided by the inductor in Laplace domain. In Laplace domain. So basically, if there is an inductor between A and B, right? So how will you replace it in impedance in Laplace domain? Impedance in Laplace domain. So this L will be replaced with LS, right? Now if inductor is having some initial current, so what will happen? So similarly we will solve. So this line I am writing VL of S. Okay. So VL of S is equals to S, not S, sorry, it will be L into L di by dt it is. So L di by dt it is. So S IL of S minus IL value at t equals to 0, right? I should have written small IL of t, right? So VL of S is L S I of S minus, what is the value? That is I naught. So it is having initial current I naught, right? So VL of S is L S I of S IL of S. So why L S IL of S minus Li naught, right? So this is the first expression we get. Also we can, this is one expression, also we can replace it with IL of S, that is VL of S upon LS plus I naught by S. Two expression we get here. This is the first one and this is the second one. Okay. So by that we can write down our final model. So basically this is the condition A, B. This is an inductor which is having an initial current of I naught. This we are calling, no, this we are calling ILT and this we are calling VLT. So if we want to replace this model, okay, so how will we replace it? So tell me, what is the answer? VL of S is L of S into IL of S. That means the impedance provided is L of S. And what is the voltage value? Li naught. Right? So the impedance provided is Ls and the voltage value is minus Li naught. Are you getting this point or not? Are you getting this point or not? So how will you write? Inductor is there, I will replace it with Ls. Now if it is having initial current of I naught, so what I will do, first I will see the direction. The direction of what? This one, not this. Direction of this current. The direction of this current is from up to down, right? So I will make a voltage source from up to down minus to plus. If it is going like this, I am not going to make like this. I will make like this. Okay, this is wrong, this is right. Okay, from up to down minus to plus Li naught. Okay, okay. Also, it is not Li naught by S. Okay, this is also wrong. Many times I have seen people doing this mistake. Okay, it is not Li naught by S. Okay. Now, what do you understand by this? If it is Li naught, what do you understand? This is not a step voltage. This is an impulsive voltage in time domain. Here, this is Laplace domain. In Laplace domain, if 1 is written, what do you understand in time domain? It is delta t. If 1 by S was written, that means it was ut. So in Laplace domain, Li naught is written. So in time domain, what do you understand? Li naught into dt. So this is the impulse voltage source. Okay. So you shouldn't make Li naught by S. Okay. You should write Li naught only. Okay. So here also we have understood, we have derived, it is Li naught only, not Li naught by S. Okay. So your VL of S is equals to Ls IL into S minus Li naught. And from here as well you can get it. Right. So what is your VL of S? This is your VL of S. Right. This is your VL of S and this is your IL of S. So this is just an impedance. So VL of S is equals to IL of S into Ls minus Li naught. Right. From here you can see VL of S is equals to IL of S minus Li naught. Right. So this is your VL of S. Now there is one more way of writing it. What is that? So initially it is having a current of I naught, right? So, and the direction is from down to up. Sorry, from up to down. So it is I naught by S. And what is the resistance provided? That is Ls. Or what I can say? I can simply say that I have applied the source transformation. So voltage source to current source. So voltage source to current source. But direction is minus plus. So I will make the current should get like this, get out like this, right? So I will make the current source direction I naught by S from downward. Or you can see the I naught current, I am coming directly from here to here. So what I will see? I naught current is coming down, right? So I naught by S and the resistance is L of S. Okay. And what will be the VL of S? This will be your VL of S. And what will be your IL of S? That will be this value, IL of S. If you want to write IL of S, what you will write? VL of S by Ls plus I naught by S. So this is your VL of S. Okay. So you don't need to mug up anything, right? In the previous analysis, here if we go in this one here if we go, you can see this is a impulse, right? This is an impulse current source, right? This is not a step current source because in Laplace domain it is looking like CV node. That means it is CV node delta t in time domain, right? So this is an impulse current source. Okay. So from here to here also you can come. So from here to here you can also come, but this is our important point. So mainly we will use this one. Okay, so just take the voltage source out of it, V naught by S, and just replace the capacitance with 1 by Cs. Okay, and in this one as well we will use this one only, mainly in voltage source only, but both are important for this case. You just remember both are important. If you just consider the current source from here to here, if you come from here to here, if you come, okay, from here to here if you are coming, and if we are coming from here to here as well, so from here to this side, from this side, okay, if you are coming, so what you will see, I naught as by current source, I naught as by current source, and the resistance in parallel, that is Ls. Or from here to here if you go, just replace L with Ls and make one battery with the direction current from up to down in the direction of current, battery minus plus. Let me say it once again. In the direction of current minus plus. In the direction of current, battery minus plus. The current is flowing like this. Note this current, the initial current, I naught. If the current was initially flowing like this, I naught, I would made in the direction of current, minus plus. In the direction of current minus plus. Okay, in the direction of current minus plus. That's it. I will use this line again and again when we study RL circuits. Okay, so if the current would have been flowing in this direction, I would have made in the direction of current minus plus. If the current is flowing in this direction, I would made in the direction of current minus plus. Are you getting this point? Okay, so this is the Laplace transform. Just make sure that you don't write L naught by S. You only need to write L naught, Li naught, sorry. You only need to write Li naught because this is an impulsive voltage source and this is a step current. Okay, here this is an impulsive current source. Okay, this is an impulsive current source but a step voltage. Okay, so inductor is the friend of voltage, sorry, capacitor is the friend of voltage and inductor is the friend of current mainly. Okay, so that's how you can understand. Okay, so now we will solve a simple circuit that we have already seen. This circuit we have already seen. So now we will solve the circuit with Laplace transform. Okay, you need to comment on VCT, VRT and IRT using Laplace transform. Okay, so I will just redraw the circuit. So what will happen? This 5 will become 5 ut because the switch is closed at t equals to 0. So this will become 5 ut and this is your R, this is your capacitor C. I will just make it like this. This is ground, this is ground. This is your R, this is C and this is your IT. This will be your VRT. Let me take here. This is your VRT and this is your VCT. Now I will make the Laplace circuit. Okay, I will make the Laplace transform now. So what will happen? What is the Laplace transform of 5 into ut? What is the Laplace transform of 5 into ut? That is 5 by S. What is the Laplace transform of resistance? That is R. What is the Laplace transform of capacitor? That is 1 by Cs. Right? Capacitor will be replaced simply with 1 by Cs because it is not having any initial voltage. And VCT will be replaced with VCS. What will happen to VRT? It will be VR of S. And this current is I of S. I will just make a line. So are you getting this point? Every time domain is replaced with the S domain. From time domain to S domain we are going. Okay. Time domain 5 into ut, 5 by S. VR into T, VR into S, VRS. VCT, VCS. IT, IS. Right. And C is replaced with I into I 1 by CS. C is replaced with 1 by CS. So now I will apply KVL. Okay, I will apply KVL. Apply. Okay, it has stopped working. Yeah, so applying the KVL. Okay, So voltage 5 by S is equals to the current into resistance plus the current into the resistance the impedance provided by the capacitor, and that is 1 by Cs. So 5 by S is equals to I of S, R plus 1 by Cs will be common, so it will be RCS plus 1 by Cs, right? So your I of S would be, here I am again writing this line, 5 by S, I of S is RCS plus 1 upon Cs. So your I of S would be 5C by RCS plus 1. Okay. So what you can do, you can write it like this, 5C by RC upon S plus 1 by RC. So your I of S would be 5 by R into 1 upon S plus 1 by RC. So tell me, what will be your IT? IT would be 5 by R e to the power minus T by RC into UT. Right? Okay, wait. This would be your final answer. Why so? Because inverse Laplace, this is inverse Laplace of 1 by S plus A is e to the power minus AT into UT. Right? So this is 1 upon S plus A value is 1 by RC. So A value is 1 by RC. So this is the final answer. And this is what we got when we did it with the time domain analysis. Right? When we did it with the time domain analysis, what did we do? Initially the current is 5 by R, at infinity the current is 0. So 5 by R e to the power minus e to the power minus T by RC into UT. This is what we did, right? E to the power minus T upon tau, and tau value is RC. And if you solve it with Laplace transform, this is what you are getting. Now let's talk about, what should we talk about? VR of S. So secondly we are talking about VR of S. Okay, so what is VR of S? VR of S is R into I of S. So here I think whatever we got the value of I of S, that is equation 1. Now we will just put this value by equation 1. By equation 1, VR of S into, what is the value of I of S? That is 5C upon RCS plus 1. So it would be 5RC upon RCS plus 1. So your VR of S would be 5 upon S plus 1 by RC. So your VR of T would be, small VR of T I should write. Your VR of T would be 5 into e to the power minus T by RC UT. And this is what we got with the time domain analysis. Initially the complete voltage will come across the resistance, and finally the complete voltage will come across the capacitor. So initially VR value is 5 volt and finally it will be 0. So 5 into e to the power minus T upon tau, and tau value is RC. So this is what we did when we were doing the time domain analysis. So same expression we are getting. Now talking about what? Talking about VCS, right? Now we can talk about VCS. What is VCS? VCS is 1 by CS I of S, right? This is your VCS. VCS 1 by CS into I of S. So impedance into the current, right? 1 by CS. What is the value of the current? That is 5C upon RCS plus 1. That would be 5C upon RCS plus 1. Okay. So it would become 5 upon S into RCS plus 1. Okay. Now I will have to break it down in two parts, A upon S plus B upon RCS plus 1. This is a mathematics, right? This is mathematics. You have to break it in two parts, 1 upon S and RCS plus 1, right? Let's just assume you are having s upon s plus a. So what you will do, you will break it in two parts, 1 upon s plus a, 1 upon s plus b. Here some coefficient will come, a and b. So this is what I am doing, breaking it into two parts. Okay, so from here what do you see, a into RCS plus 1 plus b into s, that would be equals to 5. So from here what do you see, ARC plus b is equals to 0 and a is equals to 5, right? This is what we are seeing here, right? Because s component will be ARC plus b, right? S component will be ARC plus b. Too many mosquitoes, बहुत मच्छर है. So s component will be ARC plus b and constant value will be a only, right? So constant value a is equals to 5 and ARC plus b is equals to 0. So from here your b is equals to minus 5 RC. So I think I should write in a is equals to 5 and b is equals to minus 5 RC. This is mathematics, okay? You just need to solve the mathematics, nothing else. Okay, so what will be your VCS now? Your VCS would be 5 by S minus 5 RC upon RCS plus 1, or what you can write, 5 by S minus 5 upon S plus 1 by RC, and that is VC of S. Now tell me what will be your VCT. What is the Laplace inverse Laplace transform of this? 1 by S ut, right? 1 by S ut. And what will be the inverse Laplace transform of this? 5 into e to the power minus t upon RC. Don't forget to put ut. So what will happen? 5 into 1 minus e to the power minus t by RC into ut. That is your VCT. Okay. So this is your final answer, right? So this is what we got when we solved it in the time domain as well. How did we solve it? At t equals to 0, the capacitor will act as short circuit. So your VC would be 0 volt, and at t equals to infinity, it will act as open circuit. So your VC would be 5 volt. So from 0 to 5, it will rise. So infinity value is 5 and 0 value is 0. So 5 into 1 minus e to the power minus t by RC into ut. So this is what we got. Okay. So this is the Laplace domain analysis, but we will prefer using what? Time domain analysis only. That formula we remember, y infinity plus y0 minus y infinity e to the power minus t upon tau ut. So that is the formula we need to apply. Y of infinity plus y of 0 minus y of infinity e to the power minus t by RC. Okay. And many of the educators solve many of the circuit by Laplace transform, but we will understand those circuit in time domain analysis only. Okay. So from next lecture onwards, we will see those circuits. So whatever the concept that we have already learned, that will be used in those concepts. Okay. The concept that we studied here was these concepts, like replacing the resistance, parallel combination of RC, series combination of RC, right? The concept, this concept, and also the infinite current concept. So all these concepts will be used. Okay. So these concepts are not really taught. This concept is taught of Laplace transform, but to solve the circuit in time domain analysis, that concept is used. So we will solve this circuit in the next video, and we will understand what is, how the current is flowing infinite, and if the current is flowing infinitely, so how we should solve the circuit. So everything we will understand, and I will not solve by the Laplace transform, you will solve by the Laplace transform, and you will get to know we are getting the final answer. But if you solve it directly without understanding the concept of infinite current, or without knowing the how to replace parallel RC and series RC, then you can't solve this problem. So many of the educators I have seen, all the educators solve this question using the Laplace transform, but we will solve this question using time domain analysis, and that we will see in the next video. Okay, these kind of circuit in time domain analysis. So every first order circuit will be solved with time domain analysis. You will never have to use any equation, you will never have to use any Laplace transform. Okay, so in the next video we will see that. Okay, so next video will be very important. Do watch that video. Okay, thank you.